during the talks this morning and this afternoon, about half the talks mentioned k-means. So it's only fair that we talk about it in a little bit more detail. Just to get a show of hands, how many people know what k-means is? How many people have implemented k-means? How many people have done it more than once? Good. Okay, so then we're on the same page. What is k-means? Well, it's a clustering algorithm. We're clustering points into groups, right? If you don't know what k-means is, it's about 60 years old now. So the first publication's from 57, although it didn't appear in print until 1982. But you can talk to Bell Labs about why that happened or not happened. So how does it work? So here's an example. We have 9 points. We're going to try to cluster into 3 clusters. The red one, the green one, the blue one. How does it work? We start with some set of points as initial clusters. Let it be random for now. We'll talk about why that's a horrible, horrible idea and you should never do it. You assign each point to its nearest center. Right now, you have a clustering. So you have the 2 green points in the same cluster, the 2 red ones, and the 5 blue ones. And you say, given that this is the partition that I have, how do I change my cluster centers to be more representative? Well, I take the mean of the points, hence the name. The centers move. Now that the centers move, your assignment is not optimal, and you just keep doing this until nothing changes, right? And then you call yourself done. You say, I'm done with my k-means clustering. Here's the clustering that I have, and then you go on to bigger and better things. So what's there to talk about, right? So we know that k-means is guaranteed to converge. Right? This is relatively easy to prove, and there's some potential function that it's trying to minimize. This potential function is the sum of square distances between points and centers. It doesn't really matter what it is, but there is a potential, and that's why we know it's actually going to converge, and this is a good thing to do. Good, so what else is there? So I'm going to talk about 3 different tricks in various levels of detail. One is initialization. So Ido mentioned it in the beginning. I want to walk you through this k-means ++ approach and just show you why it's a good idea. And then we're going to talk about large data. We all love large data. We're going to talk about clustering many points and why clustering in parallel and using k-means in parallel, what are the pluses and minuses and how do you do it well. And then we're going to talk very briefly about clustering into many clusters. Right? So if my k is on order of 1,000, 10,000, 100,000, is there a better way for me to do this clustering than just the naive approach that we have? All right. So, k-means initialization. We talked about random. I looked at a few books that are outside. They also recommend random initialization. You will see this all over the web. How many clusters do we have on the slides? 4. They're pretty well separated. What happens if you do random initialization of k-means and you run it till the end? What is the clustering that you're going to get? Some of you have seen this already. Right, so here I have a green cluster, which is nice, which is what you expected to see in the top left. But the bottom left cluster got split into 2, and the top 2 clusters got merged together. And if you try to repeat this again, you're also going to get a similar kind of a representation. Right, and this is nothing against k-means, this is just a matter of how did you initialize it. If you started in a bad starting point, you didn't get to a good point in the end. Right? And so this is why you should really never initialize k-means with random centers. There are many things you can do. Any of them are going to be better than this. Right? There's a very well separated, your data never looks this nice. And here, even when it's this nice, you utterly, utterly failed. Right? You cannot present this at an exec review to anyone, you will get laughed at. So then what do? Well, you can say, Sergei, there's a really simple fix here. So we're going to take the first point at random, but now we're going to say, what am I looking for? I'm looking for really well-separated centers, centers that are very far apart from each other, so why don't I just do that directly? So I take the first point, and then I'm going to say, what is the furthest point away from anything that I found? Well, it's this blue point in the bottom right. And I'm going to say, that's my center. And then I'm going to say, oh, given these 2 centers, what is the next furthest point away? The red point on the left, that's my center, and so on. And lo and behold, I got this beautiful clustering. There's nothing else to do. Now, remember I said this is what happens when your data looks really nice. Your data never looks this nice because somebody comes along and says, this is what your data is going to look like. And you're trying to cluster this into 3 partitions because there are really 3 clusters plus some noise in here. And now what happens if you were to do the same trick of saying, I'm going to take my first point uniformly at random, and now I'm going to look at the furthest point away. You're going to be exactly picking up the noise. This is exactly the wrong thing to do. It's maybe not quite as bad as doing random initialization. If you have something to do, do this instead. But this is still not a great idea, right? For the obvious reasons, now I run k-means and I merge the 2 clusters in the middle. Again, not a clustering that you want to see. So what do? So we say, let's interpolate between these 2 methods. So one method was really good in that it was uniform over the whole data set. One method was really good in that it was sort of looking at the furthest point away, which is intuitively what we wanted to do. But we want something in between because either one of those was making too much of an arbitrary, harsh decision. Right? How do we interpolate between the 2 of them? I'm going to do the following. I'm going to say, consider the distance between a point and its nearest center as I pick points 1 at a time. And I'm going to sample proportional to the square of this distance. We'll do this in pictures and in math as well. Right? So what does it look like? Whoops. This is the algorithm. Let's ignore it. So what does it look like in pictures? I take the first point. First point I'm going to take uniformly at random. This is the point that I take. Now I'm going to compute and say, what is my distance for every single point from it to the green center that I already have? Now the point that's all the way on the far right, there this distance is large. The points that are otherwise in the clusters, for each individual point, the distance is small. But since there are so many of them in a particular cluster, combined, the probability is going to be large. And so I'm likely to pick a point from a cluster mass that I have, because there are a lot of points there, and each one has a probability of getting selected. I'm not making these arbitrary black and white decisions. Right? And now I do this again, and I say, oh, here's the blue point. I can assign for every other point, what is the square, where is the cost, what is the distance to the nearest center that I have, and this is what I'm going to sample proportionally with. And I pick a red point, and now finally I get a clustering that I want. So back almost 10 years ago now, David, Arthur, and I showed that this is actually not just a reasonable thing to do, but we can prove to you that this is a good thing to do. And we can formally show that this gives you an approximation on how good of a solution you're going to find in the end. Right? And since then, this has been implemented in most of the packages that you see. Right? So I was checking it out. So Azure has it. Cloudera packages had k-means++. MATLAB has it. You can download it everywhere else. Right? So again, my point is you don't have to use this method. There are downsides here as well. We'll talk about shortly. But please do not initialize randomly. Whatever you do, just don't. Stay away. Okay, so we talked a little bit about initialization. And we said, well, is random initialization a good idea? No, if it's uniformly at random. If I do a biased random sampling, then I get a much better solution to my clustering. So that's kind of classical stuff by now. So let's get into large data. Everybody has really big data. We want to run k-means because that's one thing that we all know and love. And we've all done it, judging by the show of hands, multiple times, multiple languages, multiple late nights. So how do I do this with large data sets? Right? And k-means by itself, if you think about it, is very easy to parallelize. All of the computations that I have, I'm looking for a single point. I'm trying to compute the nearest center. This is something that's nicely distributed across all the different points. I can do it in parallel. And then I'm saying, here's an assignment of points, and I'm trying to compute the center that best fits this assignment. Again, I can do this in parallel. And that part is easy. I'm not going to talk about that. But by now, I've probably convinced you, or at least I hope I have, that initialization is important. And what the approach I just talked about said, you'll get a very good clustering, but this is a horribly, horribly unparalleled thing to do. Right? What we're doing sequentially selecting one point at a time. And now imagine that your data set is huge, and you're selecting one point at a time, and you have to iterate over the whole data set. You're going to be here forever. And so even though the algorithm is quick and the solution you get in the end is going to be reasonably good, how do you actually do this in a reasonable manner? Good. So this is the actual algorithm. So this is just k-means plus plus from before. That said a little bit formally. So we pick the first point at random, and then we have this for loop. Right? What do you like doing with for loops? If you're in the parallel computing mind frame, we like to do them all at the same time. So this is essentially what we're going to do here. There's going to be a couple of small changes in terms of doing this all at the same time. But the main point that we're going to say is that we have this probability distribution that we computed, and we're sampling points from this probability distribution. And ideally, we pick one center, and then we update the distribution, and then we continue. Now we're going to pick multiple centers. Then we'll update the distribution. Then we'll pick multiple centers again, and then we'll do it. Right? So this is what we had. This is what we get to. Very small changes, at least in edit distance. So let me talk through this. What do we have? Again, as I said, we're going to be selecting not a single point at a time, but we're going to be selecting multiple points. So each point, independently, we're going to flip a coin and say, do I want to take this point as a potential center, or do I not? And I have some probability distribution with which I'm doing it that I worked out. Those are the details. The main idea is to say I'm going to do multiple samples at every single round. So I can do this independently. I can do this in parallel. This is an easy job. We can all code it up. Right? I'm not going to select just k points. I'm looking for k centers in the end. I'm going to select more than k. I'm going to select k times some of this parameter L that we can tune over time to see what it's going to be. But I'm going to select more than k at a time. And so what I'm really going to do is I'm going to take this giant data set of millions of points that I have, and I'm looking for k centers. I'm going to say, well, a million of points I can't deal with. Let's pretend that it's big data. But 1,000 points I can deal with. And so it's much easier for me to select 10 centers out of 1,000 than selecting 10 out of 1,000,000. So let me prune this large data set into 1,000 points first, and then I'll do something with it. Right? And in the end, so this is, first I set the 1,000, and then I recluster them, the 1,000 points, into 10. So this is known as this notion of coresets. I'm taking my very large data set, and I'm extracting the core of the problem from it. And there are coresets known for all sorts of clustering problems. This is just one example of it. Right? So how many rounds do you need? There's some math. The answer is 5. Right? With k-means, how many rounds do you need? Like 20, even though there's some math that says you need a lot more, but really after 20 you can stop, you're not going to get any improvement. Here, 5 is the new 20. So what does this look like? So here's just an example on real data that we looked at this. What am I doing here? I'm saying, how many rounds am I going to run in terms of how many different rounds of initializations do I do? If I do my whole initialization in one round, this is all the way on the left-hand side. This is your random initialization. So the y-axis is cost. The x-axis is how many rounds. If I do exactly as many rounds as I need centers, this is k-means plus plus. This is what I talked about to begin with. And so the cost is pretty low. Right? But you see that this is a nice curve that you want to have, in that I can stop relatively quickly. The x-axis is on the log scale. Right? And so instead of doing 65 rounds for k equals 65, I can stop after 5. And everything works well. There's more examples. You can tune different parameters, but really the message is the same over and over and over. I need 5 rounds. I can do things in parallel, and things just work. And this is also, I know for sure this is implemented as part of Cloudera. I don't know about Azure. I haven't checked it out. But this is a nice thing to do. So many points. So initialization, we covered. Clustering many points in parallel, we know how to do. Let's talk about many clusters. And I'm going to keep this even more lightweight because even though we're right after a coffee break, kind of late. So what do I want to do? What do you do with k-means when k is very large? Right? And first, why would k be very large? Why am I clustering? Why am I using k-means in the first place? We have deep networks. We have random decision forests. We have MDPs. Why am I using k-means? Right? And I bet if I ask people in this room, the answer is usually the same. It's simple, it's fast, and it'll give me some features that I can then throw into my more complex algorithm, and it seems to work, right? And if it seems to work, why not do it? So now if I'm doing this to do feature selection and feature engineering, then I do want these features to be rich and robust. I just don't want to predict a binary feature. I want to say, oh, here's like a 100-way feature. Here's a 1,000-way feature. And now I need K to be larger and larger. Right? So why is this a problem? Well, for every point, how does k-means work? For every point, I need to find its nearest center. This is the core of my k-means operation. Right? And now this is getting to be bad. It's getting slow, and I'm waiting for this all the time. So naive approach, linear scan. Right? So I have a point. I have 1,000 different centers. I compare distance to 1, distance to 2, distance to 3. You fall asleep, distance to 7, distance to 1,000. And then I take my second point. Maybe I do this in parallel. But maybe I take my second point and I do all of this. Right? So we can do slightly better. This is due to Elkin from 20 years ago or so. You can use the triangle inequality. You can say, well, if my center that I was assigned to didn't really move, and the other centers that used to be really far away didn't really move either, then there's no reason for me to say, oh, this other center suddenly got super close. I have a bound to say how much closer could I have gotten, and so I can save some of these operations. And so especially when your data is highly dimensional, you can save on the order D part that it will take you to compute the distance between 2 points, and you can do a simple comparison and say, you do a little bit more bookkeeping, but you can get away with this. But still expensive, still not cheap. So let's go back. Let's say, what am I really trying to do? I'm trying to say for every point, what is my nearest center? This is a nearest neighbors question. Right? If I now ask you as a nearest neighbors question, and I ask you to say, oh, if I'm going to be doing nearest neighbors queries, you're not going to say, I'm going to do a linear scan. That's silly. That's my CS 101, 201. I can do better. We have 50 years of data structures. Why not use them? And so the first thing that you come up with, and you'll say, okay, here's what I'm going to do. I have all these centers. I'm going to build my index on the centers, my nearest neighbor data structures on the centers. Right? And then every single time I have a query, which is a point, and I say, which center is this query closest to? So I query into that data structure, and I get an answer back. And I do save some processing, because instead of doing a linear scan, I get something much faster. Right? There's one problem. I have to rebuild this index every single time. And so while I totally can do this, the savings that I get is actually not going to be all that huge. So let's flip it on its head. Let's index the points. So I index the individual points that I need to build. And now what am I going to do? I take a center and I say, give me all of the points that are nearby. I get some set of points back. I compute the mean of those points. I take another center and say, what are all the points nearby? I take my set back. I compute the mean of those points. What happens if I do that? Right? I don't need to rebuild the data structure every single time. I'm using the same data structure. Am I really running k-means? I'm not. But did you actually care that I was doing k-means? You didn't. You wanted some features. You didn't really care what algorithm was there behind the scenes. You were using random initialization all the time. Right? So we're going to change it a little bit. You're probably not going to notice all that much. The quality is going to be the same, but this is going to be way faster. Right? Why is it going to be way faster? Because you probably already have an index on your data set laying around somewhere. If you're in the kind of computational advertising or web world, how do you get your search results? They're sitting somewhere in an index. You're doing some nearest neighbor query on them. Right? You can point into the same index, and now, lo and behold, you have something that's optimized. Right? So we tried this, couple data sets. You can do this on more, 1 million points each. We're trying to do them into 1,000 clusters, and we took a very high dimensional space, right? Because we're, again, doing this for feature engineering in an advertising standpoint. So if you do a simple implementation, just as I described, we got between a 2 and a 7x improvement in speed. Right? Not percent, but actually times. And if you work quite a bit harder and do some caching tricks and do some more optimizations on top of it and everything else, you can actually drive this another 5 to 10x. So you can get huge improvements in your speed, while your quality, there's no degradation at all. Your objective function in terms of quality remains the same. Sometimes it gets better, sometimes it gets worse, but you get this magnificent improvement. And you're reusing the structures that you already have. So this is what I want to end with. So k-means 60 years on, at least 59 since it's been published. But it's like a fine wine, right? It just gets better and better with age, because we discover more and more things about it that the guys in Bell Labs in the 50s had no idea. Right? If you probably asked Lloyd, or if you ask McQueen, would you be still using this algorithm 60 years from now? They'd be like, dude, we just got the transistor. Things are going to be amazing 60 years from now. And they are, but we're still using k-means. So why is that? Well, we're learning more and more about it. So we have better initializations, we have parallel implementations, we can do it faster, we can do it cheaper, we can do it better. And Ito this morning talked about sort of the new direction, which is how do we do this online? Right? When we have to classify one point at a time, you don't have much space. How do you do this? How do you do this well and efficiently? And it's early on. So 60 years later, we're just starting. Lots of more work. Outliers are a particular nasty thing that we need to worry about and talk about. So this talk in particular was based on 3 papers. Those are the 3 papers right there over the past 7 to 9 years. And that's it. Thank you.